Welcome back to another video series from BJB. If you're trying to learn how to cast your own parts for prototyping or production, learning how to make a two-part silicone mold is an essential step. It's amazing to think that you can cast anything from small, simple geometry parts to large, complex parts like this electrical housing cover. BJB offers a wide variety of casting materials, ranging from flexible elastomers to rigid plastics. We also have clear or tintable systems, as well as castable rigid and flexible foams. Some of our silicone mold materials have even been used to cast low-melt metals for jewelry or foundry parts. But to be able to cast any of these things, you first need to learn how to make a mold. In this video, we're going to go through making a simple two-part silicone mold and give you some tips and tricks along the way. Our goal at BJB is to take the mystery out of the materials. So let's get started. So to make a silicone mold, you first need to start with something to take a mold from. We call that the master. A master can be made from a variety of materials and methods, but the material you make the master from can have implications on the type of silicone you plan to use for the molds. For example, there are certain types of clays, paints, organic rubbers, and resins used in 3D printing that can poison the cure of a platinum-based silicone. We'll go over this in more detail later on in the video. For this demo, we're going to use a 3D printed rapid prototype part. This part has been primered and painted with a clear catalyzed automotive type paint. In order to add a raised logo feature on our finished cast part, we added vinyl decals. You'll find that the level of detail silicones will capture and reproduce from the master is superb. Details down to an oily fingerprint or the slight thickness of a vinyl decal like this. It will also reproduce matte finishes or the high gloss of our shiny clear coat. One of the first tasks to do in preparation for mold fabrication is to determine which side of the part to mold first and how you plan to orient it. Our fire helmet is fairly flat on the bottom, and the top is the cosmetic surface we wish to display. We also look at the geometry and the features that may trap air in the part if it's oriented the wrong way. For example, these sharp points on the badge would be best oriented downward to avoid trapping air. This means that we should cast the part inverted and add the vents in the fill port to the bottom surface. This works out well because you typically don't want any trim marks from the vents and fill port on the cosmetic surface of your cast part. An important step in the preparation of the mold box is mounting the master to the splitter board, which will ultimately divide the two halves of the mold. A few common methods to secure the master to the base are double-sided tape, cyanoacrylate glue or super glue, and non-sulfur containing modeling clay. You may have to consider the finish of the side you're laying down and if that fastening method may affect that finish. We have a shiny surface on the bottom that we want to replicate. So to avoid marring the clear coat when the parting flange is removed later in the process, we'll use the double-sided tape. Now, before we permanently mount our master to the board, I want to make note of the fact that this empty space underneath the crown of the helmet will cause our master to naturally be buoyant. This can be a potential hazard if, after you pour the silicone, the buoyancy is strong enough to dislodge the master off the splitter board, ruining your mold. I can easily resolve this issue by filling the void with some modeling clay or by casting my mold silicone in the cavity, making a removable plug, which is what I did here. Let's go ahead and apply our double-sided tape. Using scissors, I cut thin strips using my double-sided tape. This tape is really aggressive, so I only need a thin perimeter to hold the master down to the splitter board. Next, I measure and mark with a pencil where I want my master to be mounted. Not making guides increases the risk of mounting the master crooked or off-center. I peel the backing off the tape and carefully place the master on the splitter board, applying firm pressure around the perimeter to ensure it's fully seated. Our master is now tightly fastened down to the splitter board with double-sided tape. You can see that the rounded edges form an undercut, which could potentially trap air. I'm going to fill in this area using modeling clay and trim it using a clay shaping tool. I've rolled the clay into long, thin pieces and carefully pack it into the undercut. I then use my clay shaping tool to further pack it in. Once that's done, I trim the edges flush, eliminating the undercut. This clay will also seal the master to the base, preventing silicone from leaking under the master. The clay fillet will represent how the second half of the silicone mold will wrap around to define the actual split line. This means that there will be a feathered edge where the second mold half meets the first. Over time, this feathered edge will degrade faster, but may be fine for parts that later get sanded and painted or not cosmetic. Our plan with the fire helmet is to pre-pigment the polyurethane and demold the part with minimal cleanup, simulating an injection molded part with precise parting lines. There is a way we can make a more substantial, defined edge that will last longer. Using materials like styrene sheet, we can form a split line exactly where we want it. Styrene is easy to cut and form and is available in a variety of thicknesses. This takes more time to set up, but will produce excellent results. The styrene can be fastened with glue or double-sided tape, and any minor gaps can be filled in with our modeling clay. There are two common methods you can use to make alignment keys for two-piece molds. The preferred method is to pre-mold them into the first half of the tool. This allows you to use a variety of shapes and materials to produce a locking system that fits your needs. We're going to be using some ABS plastic bar stock for our mold keys to ensure proper alignment of the two halves. A second method that is common for folks wanting to make quick molds is to wait until the first half of the mold is cured and hand carve alignment keys into the mold flange using a sharp hobby knife. You'll be free to carve a variety of lines and curves to suit your mold, and the shapes will be transferred to the second mold half, like this example. In order to cast a block of silicone over the master, we need to build a containment box to hold the silicone in shape until it cures. The choice of materials for a mold box is open to preference, but we typically recommend plastic, metal, or sealed wood like this shelving board material. For smaller molds, some people even use building blocks to easily form a quick and easy box. Large diameter plastic pipe is another convenient material to use. The ideal surface should be smooth, clean, and have low porosity. While it's true that cast silicones don't stick to many materials besides itself, it can form a mechanical lock if there's a rough or porous surface, so keep that in mind. We've constructed a two-piece box set from ABS plastic sheet. The height of the two pieces is deliberately calculated to allow a minimum of a 3/4 inch wall thickness all around the sides of our master for our silicone mold. The second, smaller box will ultimately help form the lid of the tool. We'll also use a minimum thickness of 3/4 inch to prevent distortion under its own weight and to accommodate the fill port and air vents, which we'll talk about later. Making the walls too thin on the mold increases the chance of distortion or tearing once it's in use. On much larger tools, the mold box is often incorporated into the silicone to maintain its shape and provide extra support. This means you can easily use clamps to hold the mold closed during casting. Once you have your master and alignment keys in place, we need to secure the box to the base. The simplest method is to bond it down with hot glue. Our box sits tightly on the splitter board, so a continuous bead of hot glue around the perimeter will secure it down nicely. Choosing your silicone is another important step in the mold making process. First, there are two categories of silicone systems BJB offers: tin catalyzed and platinum catalyzed. A very basic distinction between the two systems would be that tin silicones are known to be more user-friendly. They're typically low in viscosity, making them easy to mix, pour, and evacuate the air bubbles you stirred in while mixing. The most notable property would be that they cure well against a wide variety of materials you may have produced your master from. Platinum silicones come in a much wider variety of hardnesses, from extremely soft to very firm. But platinums can be more temperamental about the types of surfaces you pour them up against. Certain clays containing sulfur, natural rubbers, enamel and latex paints, some resins used in 3D printing, and tin catalyzed silicones are just some of the materials that can cause curing issues for platinums. It's always encouraged to run a small test on an unknown surface to be sure. In many situations, an acrylic sealer coat has been a good fix to prevent curing issues on questionable surfaces. The advantages of a platinum over a tin silicone would be that platinums have much higher temperature resistance, are more dimensionally stable over time, and can have a wider variety of polyurethane chemistries cast into them. For example, BJB's flexible elastomers and water-clear polyurethanes can have curing issues in a tin silicone mold, but will cure fine in a platinum. You can read more about tin versus platinum in the Silicone Handling Guide on BJB's website. For our project, the part has fairly simple geometry, but there is an area on the helmet badge that will have an undercut, requiring some flexibility upon demold. We've chosen the TC5041 Platinum Silicone, which has a 45 Shore hardness and excellent tear strength. This product has relatively low viscosity for easy pouring, and when cured produces a firm yet flexible end product. We have measured the inside volume of our mold box, and subtracting the master's volume we get 71 cubic inches. Dividing that by the density value of 21 cubic inches per pound found on the data sheet means that we will need a minimum of 3.38 pounds of silicone to fill the cavity. The TC5041 has a mix ratio of 100 parts A to 10 parts B. I typically like to mix up an extra 15 to 20% of material to allow for small variations in the calculations and material residue that clings to the containers in the mixing process. Not mixing enough is inconvenient, and mixing too much is wasteful. Once you've measured out the A and B, it's time to mix. Note that we're using the double mix method described in our video, how to properly mix two-part resin systems. It's important to note that we're also using a mixing container with plenty of room above the liquid to allow for expansion when we begin to pull vacuum on the mixture. Although this silicone is relatively low in viscosity, you will achieve the best results in mold quality and longevity if you de-air the silicone before casting it. The ideal vacuum de-airing system would consist of a pump that's capable of pulling upwards of 28 to 29 inches of mercury and have a minimum rating of 5 to 6 CFM. One of the common technical issues we frequently run into is that the end user is using an inadequate vacuum pump. While pulling vacuum, the bubbles will accumulate and grow in size, creating a foaming head. Be prepared to break some air into the chamber to prevent the foam from overflowing. This may have to be done several times before the largest air bubbles break and the mixture settles down. Continue to pull vacuum for several minutes, depending on the viscosity of the silicone, your work time, and the strength of your pump. Now, you're ready to pour the first half of your mold. Pour a thin stream of material on the flange and not directly on the master. The silicone will flow slowly over the master, displacing air as it rolls across the surface. This method will prevent air entrapment and produce a high-quality mold surface. Continue filling until you reach the top level of the box. After an overnight cure, we begin to remove the splitter board from the bottom of the mold box. Note that I purposely used a thinner piece of plastic supported by a thicker piece of MDF wood. Being able to flex the splitter board makes it much easier to peel away from the aggressive double-sided tape holding things together. Once that's gone, I remove the styrene sheet, alignment keys, and trim any silicone flashing with a sharp hobby knife. The last thing to clean up is the oil-based clay used to seal gaps. Before we can pour the second half of the mold, I need to apply my mold release to the exposed silicone. I'm going to use an Aerosol Spray mold release designed for silicone to silicone applications. The reason I'm doing this before adding the vent and fill port details, which we'll discuss next, is that the aerosol spray can impart a surface texture. I don't want to disturb my shiny finish, and if I put the vents on, it makes it more difficult to shield the master from overspray. So I'll carefully cover the master using the styrene cutout I saved and release around it. The aerosol cans do a good job of applying a uniform mist coat of release, but details like our alignment keys can present a challenge due to their depth and inside angles. An easy way to deal with this is to spray onto a separate surface and manually apply mold release using a small acid brush. I'll also brush around the edges of the master to ensure I have coverage right up to the split line. At this point, we need to discuss adding air vents in the fill port. As mentioned with other topics, there are a variety of materials and methods you can use. Some common things used are bamboo skewers, toothpicks, and round plastic rods shaped to your desire. You need to consider their size and placement around the part's geometry to accomplish the purpose of the vents. First and foremost, the purpose of channeling air out of the mold. But another purpose of the vent is to provide a small reservoir of what we call makeup material from any natural shrinkage. As casting materials cure, they do exhibit varying degrees of shrinkage depending on the formulation and the actual mass of the part. Thicker cross-sections naturally have higher shrinkage and smaller sections will have less. The makeup material in the reservoirs will help feed the part as it cures and prevent issues with material starvation. A good rule of thumb is to keep the width of the vents similar to the wall thickness of the part. We can also add risers to the vents to provide more makeup material in a small cross-section and to prevent making a mess from the vent spilling over during filling. We see a lot of technical issues associated with people making their vents too large in mass and subsequent problems with their molded parts, so take note. For our vents, we use these acrylic rods that conveniently have the same diameter as plastic drinking straws, commonly found at the grocery store. A side benefit is that the straws will actually decrease the wear and tear in the mold by shielding the silicone from the casting material. The tip of the vent is typically narrowed down to a point or thin tab, making it easier to remove upon demold. Consideration to the shape and size of our fill port will be based on a couple of factors. The method we plan to use to fill with, gravity fed through a funnel, syringe, or equipment injection, and the viscosity of the casting material. For lower viscosity systems, you can get away with using a finer point on the end of our plastic rod. On higher viscosity systems, we need to dull the point in order to create a wider point of entry into our mold. Placement of the fill port and vents is a critical detail in mold design. The ideal way to set it up is to place the fill port at a convenient low spot on the master and vent the mold on the opposite end. Since the brim of the helmet is flat, there really is no low spot. Tilting the base of the mold to force one end down and the other end up is the easiest solution. But if I tilt only in one axis, I can still end up with trapped air on this flat edge. So I'll rotate the axis slightly to force this corner to be the high point and arrange the fill port and the vents strategically. Using a pencil, I mark where the fill port and vents will go. I put a small drop of superglue to the points of the plastic rods and attach them to the master. While I would probably be fine with just one vent on this part, I'm adding an extra vent to aid not only in air removal, but to provide makeup material for the part. Allow ample time to cure before pouring your silicone. Before positioning the mold box for the second half, I put small drops of superglue on each corner of the lower box frame. To prevent silicone leakage at the mating surfaces, I run a bead of hot glue around the perimeter. Now we're ready to measure, mix, and pour the silicone for the second mold half. We vacuum the air out of the mixture, roll the liquid around in the container to dissipate any minor bubbles left on the surface of the liquid, pinch the can to form a convenient pour spout, and begin to pour a thin stream of material onto the flange, being careful not to induce any unwanted air bubbles. Continue pouring until you've reached the desired level of the mold box. After the silicone is cured overnight, we begin the process of removing the vents and fill ports. A twisting action and a light pull upward releases them with little effort. Using a plastic wedge, I slowly force the two halves apart. Once the majority of the surface is loosened, I manually pull it apart the rest of the way. I remove the lower ABS mold box by splitting one corner and working it free from the silicone. To remove the master, I first loosen it by flexing the surrounding silicone. Once that's done, I gently pry the master out, being especially careful of the front shield due to negative draft angles. The second half of the mold is thinner and easier to pop out of the ABS mold box. Flashing is removed with a sharp hobby knife to help clean up the edges. Our new mold is ready to cast its first part. The pigmented polyurethane is poured into the fill port, flows through the mold, and up the risers. After a few hours, the part is ready for demold. The polyurethane part cast from our mold turned out terrific. The high gloss finish from our original master has been replicated, and the subtle raised surfaces of our logo looks great. You'll also notice that our mold produced a part with almost zero material flashing, thanks to our precise parting lines. And now you know how to do it too. We hope you've enjoyed watching our video. Be sure to check out BJB's website for additional videos and for BJB's high quality casting and mold making products.